In this video I'm going to talk about extending the arithmetic derivative to negative numbers. So basically a reminder, so arithmetic derivative is a function from natural numbers to natural numbers, defined by two properties. So first is that for any prime number p, we have d of p is equal to 1, and second, for any natural numbers m and n, we have d of m multiplied by n is equal to d of m multiplied by n plus m multiplied by d of n. So this is the product rule, similar to the product rule for just the regular derivative like of functions in mathematical analysis. So first let's notice that d of 1, so let's calculate what d of 1 should be equal to. So if we set m is equal to 1 and n equal to 1 in the product rule, then we get d of 1 multiplied by 1 is equal to d of 1 multiplied by 1 plus 1 multiplied by d of 1, right? So from this we conclude that this is d of 1, this is d of 1, and this is d of 1. So basically d of 1, if we move everything to the right hand side, d of 1 is equal to 0. So that is the first conclusion. So now if you want to extend it, now the goal is to extend basically the this function d, the arithmetic derivative, to all integer numbers including 0 and negative. So first is to so like we want to extend it to keep the product rule, so that the product rule would hold for all integers, right? So the first we are going to find d of 0. So d of 0, what it should be equal to. So like we said, m, so in the product rule we set m, so like the product rule technically holds only for, like in the original definition, it holds only for natural numbers, but now that we want to extend it, so we want to find how to set d of 0 so that the product rule would hold for all integers. So we set m to 0, and n we keep as a parameter. N can be any. So like again, I want to stress that I'm not setting m to 0 in this property for the in the original definition, because this holds only for natural numbers, but I set it to the product rule if we extend d to all integer numbers. So it can be that like it could be in theory that it's impossible to extend it to negative or even to 0. So like so it could be that we would get some kind of contradiction when we set that, but we want to find at least the necessary condition for now. So when we set m to 0, so then we get d of 0 multiplied by n is equal to d of 0 multiplied by n plus 0 multiplied by d of n. So this is 0 because 0 multiplied by something, this inside the argument is 0. So what we get is basically d of 0 multiplied by n minus 1 right? So when we move this term to the right hand side, is equal to 0. So, and this can hold only, so this is for any n, any natural n. So let's write for any natural n. So this can hold only when d of 0 is equal to 0. Because like if n is not equal to 1, and there are plenty of natural numbers not equal to 1, then this term is not 0, and so the only way for the product to be 0 is for d of 0 to be 0. So that is the necessary condition. So but if we set it back, so if you go back here, so we notice that if we set here like so like going backwards, basically, if we assume that the d of 0 is 0, then the product rule would hold for 0 and any n. So when one of them is 0 and n is any number, then this product rule would hold. So now basically extending to the negative numbers, we said that d of minus n is equal to minus d of n. So this is how we define this is how we define it. So for any natural number n, so any positive n, we define it this way. And so when we define it this way, we need to verify that the product rule would still hold. So so now we need to verify that for any m and n is like in the integer numbers, for any integer numbers, the product rule would hold. So we said basically, well, we need to consider several cases. So when one of them is 0, when both of them are 0, and when one of them is negative and the other is positive, and when one of them is and when both of them are negative. So there are several cases to consider. So when one of them is 0, so this is basically we would get this, right? And the other one, n, can be positive or negative or 0 as well, it doesn't matter. Because we define d of 0 to be 0, so then this would hold true, this would hold true, so then this would hold. So when one of them is 0, at least one of them is 0, like this is easy to verify. Like I'm not going to write it again, but like it's basically writing this again. So this case is clear. So basically what remains is like there are two cases basically to verify. When one of them is positive and the other is negative, and because of the symmetry we can assume that, let's say, m is negative and n is positive. And another case is when both of them are negative. So let's consider these cases. So when So when m is negative, so we write that m is equal to, let's say, minus m0, when m0 is positive, right? It's positive meaning like it's natural number. Positive, and m0 is natural number, and here n is also a natural number because it's positive. So so the product rule that we need to verify is basically becomes d of minus m0n. We need to verify if it's equal to minus, not minus, but so d of minus m0 n plus minus m0 d of n, right? So this becomes so this is equal to minus d of m0n, right? By definition, we defined, like, this is basically the definition for negative numbers. This is equal to minus d of m0, and that's it. So now on both sides we have positive numbers under the argument, like in the argument of d. So this like we should be able to verify this. So if we simplify this equality, so this we can expand now using the product rule for natural numbers. So we can use the product rule for positive numbers, right? So this would be minus, and then we write d of m0 n plus m0 d of n. Yeah, and now we simplify this. So if we now expand this minus, right, so it would be minus d of m0 n minus m0 d of n, and we can in order to have the same expression as on the right side, we can rewrite this as minus m0 d of n, right? So now we have exactly the same expressions here and here. Right? So so this equality holds. We can remove the question mark. This equality holds. So this case is proven when one of the number is negative and the other is positive. And so the other case remaining is when both m is negative and n is negative. So in this case we basically do similar thing. So we set m to minus m0, where m0 is natural number, positive, and n is equal to minus n0, where n0 is also a natural number. And so now we need to verify the product rule, which would look like d of minus m0, let's write this way, minus m0, minus m0 multiplied by minus n0. We need to verify if it's equal to d of minus m0 multiplied by minus n0 plus plus minus m0 multiplied by d of minus n0. Right, so now we simplify. So this is equal to d of m0 n0 minus, the two minuses are canceling each other, so this is equal to basically so let's do it step more detailed. So this is equal to minus d of m0, and this term is equal to minus, so minus and minus cancel each other, so we have basically d of m0 multiplied by n0. Now this is equal to minus d of n0 by definition, and this term is equal to, again, minus and minus cancel each other. It will be plus m0 multiplied by d of n0. So, and this we expand by the product rule for natural numbers m0 and n0. We can use the product rule for positive numbers. So we get here d of m0 multiplied by n0 plus m0 multiplied by d of n0, right? So we see that the expression on the left hand side now is exactly equal to the expression on the right hand side, and so the equality holds and the question mark we can remove it. So yeah, so this proves the second case, and so basically all cases are proven, and this proves that so this proves that under this definition, for negative numbers and for zero, this extension of the function d to all integers, the product rule would hold.